All right, we're live, we're connected, testing, the audio should be good. Hopefully, we're all turned on there. Good. Wonderful, wonderful, wonderful. Hello! Welcome to the stream. Another week, more Haskell hacking action. I'm your host, Agent Ultra. And, yeah. So on this stream, I basically program stuff in Haskell. Not all the time, but pretty much all the time. And this week, we're going to learn a little bit more about wave function collapse. It's a procedural generation algorithm, fairly popular since about 2016 or so, so it's not super new or anything, but it's very, very useful. And yeah, I just thought it'd be something fun to try and implement. I don't think I've done it in Haskell, so yeah, here we go. So we got a little library set up, we got some code. What we need to do is we need to take this idea of a pattern and extract several patterns from an input like bitmap of bitmap data, basically. And so, for example, if we had like an 8x8 grid of pixel data, and we wanted to generate 3x3 patterns, we're going to get all of the overlapping patterns in that input data. So let me draw this out. And that we should end up with 36 patterns in total, I believe, if we do this. Burp, burp. Like this. Here. Here. Alright. So if this goes from 0, 0, that's my 0 because I'm triangulating mouse, because I used to have a tablet or a Wacom, but I'm klutzy and I broke it. So no more Wacom for me. Drawing with mouse now. Right, so we have an 8x8 grid here, 0 to 8, and we want to capture 3x3 patterns, right? So we go from 0 to 3 here, 0 to 3 here. That'll give us this sub pattern here, and then we take one more step and we get the next sub pattern by going, say, over on the x-axis by 1, and we get the next 3x3 pattern here, and so they're all overlapping. Right, we get the next one, the next step, by just going one more, so on and so forth. All right, until we reach the final one, which should be down here. All right, and then we should end up with a stack, it turns out, of about 36 of these. All right, 6 up that way, 6 across that way, 36 tiles. Cool. So this is how like wave function gets its self-similarity style kind of input. It also is how we do the algorithm proper. So this is just generating the input from our inputs. Kind of what's novel about and neat about wave function collapse. Right. At its core, it's a constraint propagation solving problem, or a forward constraint propagation solver. And that's kind of the more general term for it. So think like Sudoku or something like that, where you start with a Sudoku grid, all the boxes, like a completely empty one, all the boxes could be all the numbers, right? And you can think of them as like variables. Each box is a variable connected to some other boxes. And there are constraints, right? So if you pick a number for one of those boxes, say 3, right? No, 3 can't appear in any row in that grid that you pick the 3 in. And it can't appear in the column of that grid in which you place the 3. And it also, because the box is subdivided into 3x3 regions from is it a 12x12 grid? Or whatever it is, 9x9. Anyways, and it can't appear in that sub box either, right? So you have to go through to all the connected boxes and eliminate 3 as a possibility from those. That's like the propagation step, right? You kind of as I'm solving Sudoku puzzles, is kind of what I'm doing. I'm kind of keeping my head like little numbers on the outside of the box, and I cross off the 3s and all the places where 3 can't appear right now. That's the same idea here with this once we get to that part of it in wave function collapse. But right now we're just trying to get those input patterns out from our source. So I think I've done a little more research on this. I think I understand how this is going to pan out and how this is supposed to work. But we've got to write some code here. So we got this pattern idea. It's got a size to it. So we want a square pattern generally when we're working with this. And this pattern size can be 1, 2, 3, whatever. And then we get an array of some data. Right? We're kind of like abstracting over what that data is. It's just some. All right. Now, I think what I was getting confused on last week when I was working on this was I was thinking like there was going to be like a sample in the middle of our little pattern, and that all the neighbors of that sample were going to tell us the edge information. Still kind of true. However, we're going to follow this overlapping pattern thing that we're going to extract out from our input. So right now I wrote this kind of function bitmap patterns. It takes a pattern A, a word size, and generates a list of subpatterns from that input pattern. Because I'm not exactly sure how we're going to get the pixel data from whatever library we end up using to do like the graphical part of this and like interact with images. If we're going to just use an image library, if we're going to use like a game library like SDL and use its image libraries and like all the formats of that kind of stuff. So yeah, I'm thinking like a big pattern, sub patterns. There we go. We could also just change this to an array of A's, which is ultimately what we care about with the input pattern. We don't care about anything else in it, as long as it's an array of the right dimensions. Alright, so we'll just call this patterns. Yeah. Yeah. And we'll call this data. No, image data. Input data. Subpattern size. Right? Cool. Now, as we're going to go over this array, how are we going to iterate over it? All right. We know, I think we can probably pre-calculate all of the indices for the pattern we want to get, if we think about it a little bit. All right. So we want to get an 8x8 grid. All right. Burp, burp. All right, depending on our input size of the pattern, our subpattern size, we're going to get a certain amount of patterns. If we had a 1x1, it would be 8x8 or 64 subpatterns. All right. I'm going to do that in blue there. So our subpattern size, if we had 1x1 subpattern size, that should equal 64 subpatterns. And if we have a 2x2, right, we get... Right, do we have this? Not necessarily, because they're all overlapping, right? So let's see, we get... one. Yeah, I actually have this drawn out here by hand. Yeah, we get 1, 2, 3, 4, 5, 6, 7. We get 7 on a... We get 7 by 7. All right. So that makes 42. And we already know 3 by 3 because I already calculated that one out before starting the stream. 3 by 3. 36. All right, 4 by 4. Can we guess what that one's going to be? All right, 4 by 4. Can we figure out what 4 by 4 is going to be? Can we predict what it's going to be? All right. 1, it's got all 8. 2, it had 7. 3, we got 6 on a side. All right. 4, I'm guessing we're going to get 5 on a side. All right. 5 times 5 is 25. All right, and then we have 5 by 5. All right, we got 4 on a side. 4 times 4 is 16. 6 by 6. What do we get here? 3 by... we get 3 and 3. So that would be 9. 7 by 7. What do we get here? All right, 2 by 2. So we get 4. What are we going to get for 8 by 8, though? We should just get 1. This is the whole thing. All right. So that's what we gotta pull out. And Cypher 1024. Yeah. Welcome to the stream. Thanks for stopping by. It's nice to see you again. I don't know if that's the exact formula. Alright, so we're trying to get the overlapping subpatterns of an n by n square from this square. And extract those into our pattern data structure here and get the subarrays, essentially. Alright. So, in the 1 by 1 case, it's all 8. In the 2 by 2 case, it's 8 minus 1. Actually, that might work. Let's do just some quick calculations in the REPL here. Oh, no worries. We're working on wave function collapse, which is an algorithm for procedurally generating images. Yeah. And so we're working on a subpart of that right now, which is... so at its heart, I'll explain this one more time, quickly. At its heart, wave function collapse is a forward propagation solver. And what's kind of novel about wave function collapse is that you can define the input constraints from a source image by cutting out these overlapping tiles. And then as you're generating the output image, you use these tiles, and then they already have the constraints built into them of what tiles can go next to them. So it generates kind of self-similar, locally self-similar images, output images from the source input image. So we're working on the step, we're working on the part of generating the input to the algorithm. All right. So if our size of our grid is 8. All right, so then plugging in Cypher's formula here, we'll give it a shot. All right, is 9 would be grid size plus 1. And we'll use lots of parentheses here. Minus grid size. Square root of 2. 1. Oh, n is our size. So if we do 2 by 2 square, not quite. 49. All right. Is this the right result? Right. Let me skaboosh. Let's draw out a grid like this. We go 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. Wait, 1, 2, 3, 4, 5, 6, 7, 8. Okay. 1, 2, 3, 4, 5. So we got 1, 2, 3, 4, 5, 6. Wait, 1, 2, 3, 4, 5, 6, 7. And a little column here. There we go. Hey, tech support. How's it going? Welcome to the stream. Nice to see you. Yeah. Yeah, I haven't really touched this kind of stuff in a while, so that's why I like to do this stream too. Part of the reason why I do it. Okay. Right, so in the 1 by 1 case, it's just the sub pattern is just one grid, one pixel, right? So there'd be 8 by 8 of those. I think that one's right. All right, so there should be 64. I think we can agree on that one. 2 by 2 then. All right. Let's say that's this little subsquare here. That would be one pattern. All right. We also want to get this pattern. This pattern. This pattern. This pattern. This pattern. And this pattern. All right. So that's 1, 2, 3, 4, 5, 6, 7, right? So there's 7 here, and there's 7 this way. All right, so that would be 7. So the 2 by 2 case would be 7 times 7, which would be 42, right? Right? Pretty sure I'm right. I don't know. I should be right because I'm helping my son with his times tables, and if I'm messing that up, nope, it's 49. Oh, yep. See, I'm super smart. I'm really helping my kids with their math homework. Okay, so it is 7 times 7 though, which is 49. Okay. And in the 3 by 3 case, right? We said there was going to be 6. 6 was going to be our number 6 here. So like that's 1, 2, 3. That's 1. That's 2. That's 3, 4, 5. Right, I miscounted these. All right, there's one group of 3 here. Group of 3 here. A group of 3 here. There's a group of 3 here. Here. And here. That's 1, 2, 3, 4, 5, 6 of them. 6 by 6, 36. Okay. All right, so this formula we had, the 2 by 2 case, 49. We plug n to be 3 by 3, we get 36. If we get 4, we get 25. think that was right. 5, we got 16. Yes. 6, we get 9. 4. 8, we should get 1. Yeah. Wonderful. What's our formula? So then we know how many there are going to be, and so we just have to generate all the coordinates for those patterns using that information, and we should be able to get the indices we need to get the subarrays out in our patterns function, I think. Kind of my approach there. Let me just get rid of all this and start here. So let's see. Num patterns, maybe? All right, we gotta get our input array size. There's gonna be, we know it's gonna be square, even though the type doesn't say so. Maybe we should have a new type wrapper for this. Just to have that guarantee in there, because that type doesn't really say much about that, but yeah. Maybe we could do that quickly. So if we get the grid size of that, in fact, maybe I'll just pull that over from the REPL. No. Emacs. What did I do? I didn't want to exit. So I'm on a new keyboard. I also broke my old keyboard, including my Wacom tablet. But Wacom tablet I broke a long time ago. Keyboard is a new fresh wound. Anywho's, here we go. We're gonna paste that over there. So we gotta get the grid size, and then n we gotta replace with our subpattern size. And there you go. So, something here. Yes, I'll figure out grid size in a moment. So, what we can now get are the... let's see, the coordinates of where we're going to do all this subarraying stuff. Pattern chords. All right, that's going to be a list comprehension. And it's going to be squares. No. We have to get the x and y each for up to num patterns. So we're going to get the tuple of x and y's into our array matrix. For x, it's going to be in range 0 up to subpattern size, or num patterns. And y in the range 0 up to num patterns. Okay, pretty reasonable. All right, and that should be, let me just plug that in here. So if we had num patterns of, say, 8? No. Yeah, 8. Let's do something smaller, just so it doesn't overtake my screen. 0, 3. 0 to 3. So it's going to be the same number. 0, 0, 0, 1, 0, 2, 0, 3. And that will correspond to this 0, 0 here. 0, 1 here. 0, 2. 0, 3. Here. Yeah, and this would be for very large grid size. Okay, I think that makes sense. And then we get 1, 0, 0 down 1. Yeah, 2, 3, and all the way through. Okay. Cool. And then we need to collect together the patterns themselves. We could do this with a fold over our pattern coordinates. Or could we build that right into list comprehension itself? I think we might be able to do that in the list comprehension itself. Assuming that our ability to pull out these patterns is a pure function from our input array. I would call it subpattern. Or extract pattern. X. I might want to leave it as tuples, X, Y, and pattern size. Something like that. And then we'd have to give it the array as well. So input array, X, Y, subpattern size. And that should get us the list output list of patterns. Let's pull this over here. Like that. Get rid of my terrible drawings. Okay, and assuming we can implement the things that are highlighted in red here, we should be able to fix this and get this working. Okay. I'm going to take a moment to transform this into a new type here just because I'm thinking about it real hard. We'll call it texture. Oh my god, a little wraparound. We need the A type parameter. There. Okay, replace that with texture. And then a grid size. How big is our texture? Call it texture size. And all we need to do is get the array out. And we need to get the bounds. And from that, we just need one of the elements. Say the first, and then we need to convert that to an integer. Texture size of input. I'll just call it texture. Yeah. I don't know why fly check doesn't display properly anymore. I noticed that last week. It somehow broke. I don't know what I did. I don't think I changed anything recently, but we can pop it into our REPL. Step type int with actual type word. Oh, we have, because we're defining we don't want the subpattern size to be a negative number, for example. It's not necessarily in the range of integers. We can use from integral on this as well. Okay, and then we just need extract pattern. Let's put it here. Extract pattern. Takes a texture of A. Coordinate int. And I guess an int, and then returns a pattern A. Okay. I have to do this again. Yeah. Can I implement the right type class instead of using from integral? Is there a type class that would do that? I mean, from integral is from a type class, right? All right, info word. All right. Is that what you mean, Cypher? Like, I could just make it an int, but... the exponentiation is probably num A, integral B. But that wasn't the problem. The problem was subpattern size here in my extract pattern function. Although yeah, no, it's because it's in this subpart of the formula. 2 is fine, but it needs to be an integer here because we made the front texture size here an int. Alright, and the type of minus is num A. Yeah. I still think that's kind of one of the weaker parts of the Haskell numeric stack. Although it's probably good, but it is kind of annoying to have to write all these conversions. Yeah. It's probably a good thing. It's like eating your oatmeal, you know? The same thing when I was like experimenting with the Zig programming language. It's a little bit more explicit about where conversions happen. You have to explicitly say them. And whereas like I'm used to C, where it just promotes things somewhat sanely, sort of. So it's a good thing, but yeah. I don't know. Sometimes it feels like if you can, sometimes it feels like in kind of like numeric heavy code that some of these promotions are actually kind of nice sometimes. Okay. Some coercions are implicit, and we work with multiple integral types. Yeah, integers, naturals, yeah. Cool. Yeah, I wish Haskell could do that. That would be pretty nice. Okay, so we got from integral hereward word. Oh, because we went the first of the first. We're dealing with a multi-dimensional array from texture, I think. Yeah. Oh no, we want the first of the second. it's such a small library, but I always end up having to look at it for some reason. Array, bounds. Yeah, the bounds with which the array was constructed. Right. So our bounds are going to be the lowest word and the highest word. It's multi-dimensional, so that makes sense. So the second to the highest one is what we want in order to get the size of the texture. Now, the reason why I did this type is so that we can have like make texture function that will make sure that it's always square. All right, so if you're going to make a texture, just like with the pattern, you got to have a fill value in there. It's almost exactly the same thing. Fill value. This part is going to be basically the same. Okay, and maybe we'll have, and as we proceed in the library and implementing this algorithm, is we'll have conversion functions from our bitmap type from whatever library we end up using into texture. So that should be good enough to at least to start testing things with. Okay, so that way make texture, like you can just define a word size and it's going to be a square because you don't get to just make an arbitrary thing. You can make just a square texture. We might want to change that, maybe, but for now, squares are what I'm working on. That's kind of what our formula is based off of for num patterns. Hopefully that won't be too restrictive. Okay, anyhoozle. So now we just have to implement extract pattern. Then we can start playing around with some of these things too. Okay. Extracting patterns. So we need to get some part of the subarray within the bounds that we want. The boundaries are going to be defined by this xy here. That's going to be our lower bound. And we want everything up to that plus size, that index plus size. And we're kind of trusting with extract pattern that it's within the bounds of the textures array. So maybe we should make it a sub function, like where function bound to patterns, just to make that clear. I'm just going to leave that here for now. So let's see, indices, elms, soaks, accum. Takes an array and an association list and accumulates pairs from the list into the array with the accumulating function f. I don't think we want to accumulate that. Takes an array and an association list. So this must be our accumulating function, E. So elements of array there will be the input. List of IA. So the only way to get an E is by applying this function here to get some output E's. Oh, maybe that is what we want. We'll just ignore... Almost. Almost like that. We just want to ignore the A's. We actually want the E's from the input list. It's strict in all the results of applying the accumulation. It's lazy initial values. So it should be okay to ignore the A's there. We won't build up any leak any data and build up any like unevaluated thunks, hopefully. What's Xmap? Transformations on array indices. Not quite, yeah. A Q might be good. Otherwise, we might like have to iterate over this thing with our indices and just use the accessor to get them. Okay, let's try it with a Q array. I think that might be what we want. A Q array, some function, and oh, sorry, list array. What was a Q array dot a Q. All right, some function, the input array from the texture. So we could probably just pull that out here. Just by destructuring in the argument. And then the association list. And then we need to put that into a pattern, construct a pattern from it. We got a fill pattern. Probably just use pattern, size, skadoosh. But we need some function on size to transform that into a word. Into word, we've got 2enum. Okay, 2 holes. There we go. For accumulator, we just want the arrays elements. I think. Google, is there a function that just ignores the second argument and returns the first that I can just, that's already defined? Simple, trivial to implement, but const, yeah. There we go. That's the one I'm thinking of. And then we just need our accumulation map. So this is going to be, let's see, from 0 up to size, because I think the ranges are not inclusive, right? I go 0 and say my size is 3. Yeah, oh, it is inclusive, so it includes 3. Okay. So how are we going to generate that list of a socks? We need a list of tuples. And we want a list of tuples like 0. Let's make this a bit bigger. We want like, we'll initially say 0, 0. And some dummy value we don't care about. We want 0, 1. 0. No, we need to generate all of the indices in that range. Yeah. So that means, so our input index here, xy, for extract pattern, is just the start. We need to generate all of the indexes. Yeah, for all the, okay, I think I know how to do that. So we go, something here, but we got to go in the range of size. So I'll call that Z. From 1 up to size. We don't need the 0th. That's already going to be included in our set. And we add that element to X. If we only add it to X and Y, then we're only going to get the diagonals. Right? So let's let X equals 0, Y equals 0. So we're going to start at the top left corner. We're going to try this formula. Oh, we haven't defined size, so let's pretend size is 3. Yeah, so we're just going to get the diagonal here. We want the whole box. So I think what we might actually want is to bring X and Y over to the right here. And let's call them elements A to be X up to X plus 3. And B to be the elements Y plus 3. Oh, wait. Unit. Silly. There we go. Let's go 0, 0, 0, 1, 0, 2, 0, 3, 1, 0, 1, 1, 1, 2, 1, 3. So we want a 3x3 box. So we actually need size -1 because it's inclusive. This would be properly 2, and that would get us our 3x3 box. Yeah. Okay. So I'm just going to steal this. Pop this over here. And 2 is going to be... let's put this in a let binding, I guess. Width. It's going to be size -1. X plus width, and then Y plus width. And then you take AB here, and that part, and then we put the tuple and our dummy value there. And the problem with this is... right. We convert those to words. From integers, hopefully positive ones. Our fill value. we have to get a default value here. But the reason why this is highlighted is because Haskell doesn't know, like, what the type here is in the array we're trying to accumulate. It's defaulting to 1, so it's picking 1. But we said pattern of A in the return type. So it's got to be the same A that whatever texture is given us. We could... What could we do here? Well, if texture's not empty, we could get a value from it to fill in there. Or we can change this to a fold over our array and not use texture. Because we don't really care about that value anyway, so that's probably the better way of doing this. Just checking the time. We're good. Okay, arrays. Are arrays foldable? Yes. Okay, so we should be able to transform this into fold L prime. Okay, we have to change our function. And that function is going to have to take our texture. And our starting value is going to be a list. And then we have to construct an array from this fold. I might want to do this up here. This equation is getting a little long. We'll call this texture elements. And then we can construct a pattern here with array dot array, no, what did it do? List array, texture elements, and I think list array we need to give the size, the bounds. As well. All right, a whole bunch of holes, whole bunch of red. We're going to figure this out. We're going to get it compiling, and hopefully this is the right structure. And we're on to something here. Okay. So our fold function, let's name that. We're going to call it theme elements. Going to put it int here. On purpose to get GHC to tell me what the type should be. Here's this. Okay, so again, we don't know the A's here. The inference wasn't able to figure it out either. These should be... No. Right, this doesn't need to be the default value. We can get rid of that. Okay, so it should be getting an input tuple. And these A1s should be our A's that we're accumulating the array values. We still have to figure out, oh yeah, these should be, what? Int. There we go. Or word. Actually, yeah, texture is going to be word, the indices, so let's make those word and get rid of the two enums on them. Now it's given an XY, so... Maybe we should do the same here. Those, give it this. This. Width. Okay. Cool. So list array, what's this? Yes, this whole needs to be a tuple word to word. Oh yeah, it needs to be our array bounds. So we know the first one is going to be XY or 00 is our pattern, right? It doesn't need to the original bound. It needs the bounds of what we're selecting out here, and the upper bound is going to be something. What is the upper bound going to be? How big is it going to be? Well, we know the size of the pattern, and we know the size is square. Well, Cypher, I don't know yet, which is why I put a type parameter on it. Because we might pick, say, a game library like SDL2, and it might have an image library. It has an image library, and I don't know what the primitive types are going to be that represent each of the elements in the image data. Like, they could be word 8. They might be something else. My thinking here is just like use texture as kind of a stand-in wrapper type just to get things going, and then maybe as we get further along we can actually convert from our source bitmap format, whatever it happens to be, like say it's an array of word 8, and just construct a texture from that. Does that make sense? I haven't, but we could. I think once I get this basic patterns function almost there, then yeah, there's going to be some other things that we're going to play around with patterns and stuff too. So we probably could do that because patterns in the algorithm. Let me just take a moment to diversion for funsies. So when we're laying, once we have these patterns, say it's like a 3x3 of pixel data here, then when we go to the constraint algorithm part, the constraint propagation algorithm part of the wave function collapse, the idea, the kind of a first step you do is you go to place one of these this grid of pixels onto your output source image somewhere, right? And in doing so, you collapse the array of possibilities for where we could place other patterns beside this one. So with your explanation, it might be less necessary, but if there are multiple possible instantiations, you can fmap to apply state transition functions. Ah, yes. Yes, indeedly do. And so with patterns, once you place this into the output image, a pattern, the pattern on this side, say, that we can place next to it, right, is constrained by the, it has to, the side that we want to place here, the pixels that we want to overlap there have to match. So when we place the next image, we're going to place it overlapping on this side, say, here. Like this. Right, and so after I place the blue one, right, there's only so many patterns that have the same values on their right hand or their left hand side as the blue one has on its right hand side. If that makes sense. All right. And so we collapse down the set of all possible patterns that could go here to just the ones that match this column. Right? It might also be, if we've placed one up here, it might also be the top row and so on and so forth. And so we might only get like a few that we could pick. And then we pick that one, place it, collapsing even further. If that makes sense. Right, so there's a relationship between these patterns here that we need to, that we can also play around with. Once we can extract out a bunch of them. Right, so the pattern, does a pattern match on the right hand side with another pattern? Does it match on the left hand side? Which side does it match on? That kind of stuff that we're going to need. And like the algorithm does, like people have implemented it so you can support rotations and symmetries and stuff as well with the patterns, depending on how you want to shape the output, which could be fun to play around with as well. Okay. So extracting the pattern here, list two arrays, we need the bounds. So from 0, 0 to, I think size. I think that's inclusive. So it might be size -1. I always forget this with this library. If indices on the bounds are inclusive. These bounds are the lowest and highest indices in the array, in that order. Yeah, so I guess by going by their example, 10 by 10 matrix, 1 by 1, 10, 10 might be inclusive. So it might be size -1. Okay. V3. So we just have this type error down here still, but I think that one fit. So extract pattern. Yeah, well, because we changed it to word, right? Okay. Oh, where's this one? 53 here. There we are, size. Okay. Oh, giving sizes an int again. Okay, let's be specific. Not int. Subpattern size, we don't need from integral on that. Do that. And that. That. Okay, we might have some defaulting going on. Line 60. Oh. Mm-hmm. Okay. Oh, it doesn't know that we want... So it's picking integer. That's probably fine. Can I do that inline like that? Or do I have to do that here, maybe? Allowed. Scope type variables. Okay. That one's still there. Oh, why can't it figure it out? I can't figure out the literal 2 is supposed... I meant int. Okay, well, I'll really spell it out for you. Hope that works. Okay. I don't care this missing export list. I actually don't like that warning, but there we go. Okay, so there's patterns. Okay, so if we create a texture T with muck texture, like just integers, with the integer of 0, say 255. Yeah, let's just do 255, and size, let's do 8 by 8. Okay. Ooh, that's not right. We need that to be 1. Yeah, that's probably better. Get T, texture size T is 8. Okay, good. Let's extract a pattern from it. From T at 0, 0, and we want it to be 3. Oh, we have an undefined. Where did I leave undefined in? Oh, I'm a dum-dum. I left it there. We're not done yet. Okie dokie. So we have texter, we have the accumulator, and we have the current index. Call it I and J. Okay, so we have to return the accumulator, but we're going to get the element out of array and accumulate onto it. So that looks like tech array.bang ij const onto accumulator. Okay, so we could probably just leave this as x. Okay, T, extract our pattern. There we go. Our pattern size should be 3. It is. And we got 0, 0 to 3, 3 as our bounds. 0, 0, 0, 1, 0, 2, 0, 3, 1, 0, 1, 1, 1, 2, 1, 3. That's 4 by 4. And then we're going out of bounds. Not quite right. Okay, so our width our size is too big. Yeah, so this is too big. I did it again. So we want the size, when we say 3 here, we don't mean an index, we mean a width. So yeah, that should be size minus 1. And let's check our assumption on these. I'm just going to find those. Yeah, I'm going to pull that over here. There, like that. Okay, so let's see, we got when x is 0, or let's do y. We got when y is 0, we got 1, 2, and 3. Zero, and we said width was 3. 0, 1, 2, and 3. So that's 0 plus 3. Okay. The width should be size minus 1, so it should be 0 to 2. T. Okay, there we go. It was just the size bounds parameter. Yeah, okay, perfect. Right, okay, yeah, that makes sense. Okay. Yeah, so then we got the right pattern here. So we got 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. All 2, 5. So we got the right subarray element, hopefully section, I think, from that. Cool. So then patterns should be able to take that T, and we should get our pattern size is 3. Let's call them P's. So we constructed T to be 8 by 8. So we should have P's should be the length of 60. That's too many. 1,369 was not what I was expecting. Texture size of T is still 8. Yep. Okay. Let's try some of these sub-formulas here with texture. The num patterns, what do we get for that? Replacing texture here with T, and sub-pattern size with our argument, which was 36. Okay. Oh, okay. Yep, that makes sense. So num patterns is 0 to 36. So that's not quite right. That's not what we want. We want... Yeah, that's 36 total patterns. For extracting the pattern, we just need the number of rows, columns. So we actually need the 6 by 6 part. Or counting up to 36 by, well, we don't know that. Yeah, no, so the formula for num patterns is wrong. Given the texture size of 8, we want to figure out how many or we could take the square of num pattern, the square root of num patterns, instead of squaring it. That might be it. All right, so let's create T. P's, length of P's. 49. No, this errant 1 shouldn't be in there. T and P's. 36, there we go. That's what we were expecting. Okay. So we can extract out the patterns from that. If we make these to be patterns size 1, we should get 64. And if we get a 2, it should be 49. Right. And then 3, that's 4, should be 25. Yeah. Okay, cool. $16. All right. And then if we try to do P's size 8, we should just get 1. Yeah. And if we do try to get 0, 0 is a valid word. Length of P should be 0. But it's 81. So we already have kind of a little bit of a problem with our types here. We could fix up this code a little bit. Right, so word isn't technically correct. Right, because we can't have 0. But word admits 0 as an element. So word is the unsized, I think it's the unsized word, machine word type. So like the same, but I think it's the same size as int on most machines. Word. Yeah. Yeah, same size as int. Just unsigned. Alright, so we could take an approach here where we change this out for an even more specific type. And we put a smart constructor on it. Kind of unsatisfying. X has to be greater than 0. And then we could do just size like this. Otherwise, nothing. All right, we could do that. And using just primitives. Or we could make the guard, we could put the guard on patterns. And keep word. That seems unsatisfying as well. Might just go the size route. Why not, right? Unless you got any trick cipher. Right, anywhere that we're using that, we can just use size. our calculations. We'll have to pull that out and then do all the integer conversions if we need to do any. Sorry. I was suggesting, this approach to wrapping an int in a new type and putting a smart constructor on it so that we admit only the elements we care about into our set of values. Kind of unsatisfying, but unless you have any other tricks there, that's what I was asking. Otherwise, I think I might just go with that and make the code work with sizes. Alright, so then we should probably also replace almost all of our use of word in here with sizes. Word here is still okay for our array indices. We don't want negatives. We don't actually want integers, but 0, 0 is a perfectly fine index. It's just the sizes. These might be defunct now. We might not need those. Fill pattern. All right, we're going to want a size. Yeah, that's my concern. You're always going to be unwrapping it to do math. Kind of annoying. But at the same time, like, I don't know. Like, patterns, when we use word, gets a wrong value if you use the 0 value in the set word. Right? It gets a wrong result. Because we don't expect a size of 0 for our patterns. That doesn't make sense. So the trade-off there could be that we have some guard here for the word 0, the element 0. And then everything else is fine. Right? Like, you might give 0, and then we'll say, okay, well, we'll give you an empty list then. Boolean's nothing. There's no such thing as a pattern of size 0. That could work. But we might have to, like, get clever with that in other places where we're constructing things like patterns and textures as well. Let me keep undoing all this. We'll commit this, and then we'll try the refactoring to see if we need to. Since this works. When you construct a size, where is the integer coming from? If it's input from the user, I think your way is sort of parsing. That makes sense. If it's a way of writing a precondition, I'm not sure it will do the trick. Yeah, I mean, it ultimately would come from the user, so we could parse it, and then we don't have to worry about it. Yeah, because ultimately when you run this wave function collapse thing, they could be in code, but we might have like a little program that has a little input where you can input your image, and then you have to give a number, some size of the these patterns that you want to extract out of it. Right, and so that input could have the parser on it that says, okay, well, 0 isn't valid, you can't use 0. And then we don't have to worry about it in our code. That's true. But then, like, if you want to use this library programmatically and you want to extract patterns yourself, then you know. Yeah. Alright, I was adding a bunch of tests. I don't know if those... we got very far with that. No, that's all garbage. We should add tests to these. We will, but I think there's going to be some more interesting stuff in a moment. I'm going to get rid of those, but I'm going to add algorithm in. We might have to update the Cabal file. Library, expose modules, no. Yeah, I don't want to expose lib. I want to expose wave algorithm. Make sure that builds properly. Ooh. Maybe I'm using stack for this. I should be editing that manually. Oops. That'll regenerate it for me anyway. There we go. Test spec be just that. Stack clean. Yeah, it is. It's pretty nice. Cabal's come a long way, actually. If you haven't used it in a while. It's not quite up. It doesn't have some of the nice tools that Stack has, but it's come a long way. Right, so we got rid of quick check. I need to add array as a dependency, and then we should be copacetti. There are lots of code formatters for Haskell now. Yeah, there are quite a few. I use them at work, yeah, and they're great. I don't have to think about the formatting. I don't use them in my side projects that much, because, like, I'm always switching projects, they're kind of small. I like my personal style of formatting. Just because, like, I try to keep it readable without line wrapping and stuff for the stream. When I'm splitting windows and stuff in Emacs. But at work, I just don't think about it. If there was a code formatter that formatted things the way I wanted to without me having to configure it, I'd go for that. You don't have linters and formatters? Yikes. But I guess you, like, a proof probably doesn't have a ton of code, like, as much code as a Haskell program, but it'd probably still be nice to have, wouldn't it? Quick check here, yeah, out. Yeah. Yeah, so this arbitrary stuff's going to go. We don't use record wildcards anymore. Okay. Well, we do reuse record wildcards. Why are you telling me to get rid of it? Yeah, okay. I got it. Alright. all of that. So we add patterns. Okay, we've got a little bit of time, so we can do a little bit of refactoring before I gotta go. Once you got something working, take a pass at trying to clean up the code, make it look a little nicer. It's always a good habit to get into. Okay, so the one way we could clean this up with the word thing is we could have a guard, like I was saying. We could have one for subpattern size is equal to 0, and just return the empty list. Otherwise, do the thing. Texture size. Oh, I removed. Did I remove a 2 enum from that? Oh, what did I do? It was working, now I messed it up. Oh, just ended. Just brace matching, okay. Whew. That. Cool. Right, and so if we went to go do the silly pattern, 0, right, length of piece should be 0. There we go. That's not too bad. It's pretty good. Probably better than like factoring to use word all over the darn place. Maybe. We just have this annoying case here. That's about it. Let's see. So the other thing is constructing a pattern. Patterns of size 0 actually don't make sense. Alright, so make fill pattern here would also be broken. 0, 0 here. Although the internal array would be fine. Right, but the size wouldn't make sense. Because you would say size 0 and it would be like, it actually is a 1x1 array. Like 0, 0 is a valid index in here, so you could actually get a value out of it. Even though we said the size is 0. So this one we'd have to have like a maybe on it. Where if size is equal to 0, nothing. Otherwise, just yeah. Right. So now if you want to make a fill pattern, there you go. So we always have to check for 0 with this pattern. Alright, so that's like pushing the constraint down to us to construct things properly. And the other approach when wrapping word in size is pushing the constraint on the caller. And That might work well with parsing the inputs, and a minor inconvenience to programmers who want to like use this programmatically. Let's see, extracting pattern, since we also use word for the size here as well. We also need to check for that. Which means we would have to turn this into, what, like a maybe, right? Which would kind of make extract pattern here. Well, we'd have to add one more call, basically, to this list. Like sequence or something to get all of the, or even just cat maybes. But that means we would be dropping patterns, potentially. Even though we shouldn't be if we validated it here. So the other thing we could do is we could just move extract pattern to be where attached to this, so that it's obvious, like we don't need to check the size. Hopefully it's obvious anyway. Although Qm elements might be okay there. That's going to name shadow. Yeah, it's going to be name shadowing. Where else is it? Just that spot there. So I'll just call that text. Text. Okay. That might be a little better. So this way, extract pattern doesn't really bother us too much. We've already validated that word is not 0 here. We don't have to check it again in another function. We can just pass it along knowing that it's not 0 here. That's a little better. Let's see. The texture size is good. We could make that a word. And then we might not have to have that 2enum here, at least. You could have it here instead. Move some braces there, it's a little nicer. Mug texture's fine. Fill pattern. We did that one. Pattern length. I'm not sure what we needed that one for. I don't think it's used anywhere, so we might want to just remove it. Yeah, let's just get rid of that. Okie doke. Cool. And better patterns, texture size, texture. Maybe want to move the texture stuff to a different module. We could just leave it here for now. Yeah, because we're running out of time, so let's stop there. Haven't pushed this yet, so I'm just going to squash these things together. Texture. Some data. Matrix array of some data. we extract the patterns function extracts all of the overlapping patterns for use in the wave function collapse algorithm. Okay, let's create a repo for this code so you can go check it out for yourself and follow along. Actually, I don't think I'll be able to show that, so just hang on a second. Be right back. Yeah, it's going to be a whole pain in the butt. So I'm just going to push the code up. I'll put the link on my socials, and then next week when you tune in, we'll have it up there. So it's been fun. Thanks for tuning in. Thanks for watching and follow along, and all your helpful suggestions, Cypher. It's been a pleasure. If this is your first time tuning in and you haven't, you've enjoyed what you've seen, and you haven't, seen this before, and you want to follow again, if you're on Twitch, you can set up your notifications. You can follow this channel here, and then you'll get notified when I go online. If you're watching my YouTube channel, because you're in a different time zone, you can't watch the streams all the time, you know what to do there as well. Subscribe, like, and all that stuff. It really helps out. This is my socials here. I'm on the types.pl server in the Fediverse on the Mastodons and all that. So you can follow me here to get updates on like what I'm up to, what I'm streaming about. I usually talk about tech stuff, occasionally other things. You can also find links on my other stuff like my website and things like that as well here. If you go to the link above, that is declarative.tv. Pretty cool little website put together. There's a link to a Discord server there. And the Discord server has a channel for this stream. So if you want to talk about your projects between streams, you want to ask you want to ask a question that you didn't feel comfortable asking online, you can ask there as well on the Discord server there. So happy to help, and it's always fun chatting with people there. So what else? I think that's all I got for now. So thanks for tuning in. I usually do these streams once a week on Tuesday evenings, at about 8 after 10 in the Eastern time zone. So follow in there, and I'll see you next week. May your monads always be free, and your types always check. And we'll see you again. Take care out there. Happy hacking. Brr, 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 brr.